topic of my research is studying optical properties of ferromagnetic nanostructures. And so, in a few words, they are metallic nanoelements that, thanks to their space confinement at the nanoscale, they have peculiar optical properties as metals. But in addition, since they are ferromagnets, we have an additional functionality here, which is the magnetoptical activity, which is peculiar of ferromagnetic materials. So that means that the motion of the electrons that are responsible for the optical properties can be modulated by application of external field. So compared to... Okay. So in this moment we are sending light on our sample, which is an ensemble of magnetic nanoantennas. They are nanodiscs of nickel in this case, which are randomly dispersed on a glass substrate. And in this moment we are sending red light, which is generated by a supercontinuum laser. So a supercontinuum laser is a laser source that generates a continuum of wavelengths in the visible range. And by using a filter or a monochromator, we can select continuously the wavelength of light. So we can have a very high intense red light in this case, and we are sending the light on our sample and measuring in this moment we are measuring the light being reflected back by the surface, and we measure the polarization of the light reflected, and we change at the same time the magnetization of the sample by applying a magnetic field through this electromagnet. And what we see here on the screen is actually in these first two panels, which are identical basically, we show this jump is the variation of the ellipticity of the polarization of the light reflected as we switch the field from this value, which is 1 Tesla, to -1 Tesla. So we observe a change in the ellipticity, which goes from positive to negative as we go from a positive field to negative field. And this happens when we use the red light. And this is a property that is related to the fact that we are exciting in this moment two plasma resonances, one perpendicular to the other one. One is induced directly by the incoming field, and the second one is induced by the magnetoptical coupling. So this second resonance is a peculiar effect of ferromagnetic nanoantennas. If now we change the wavelength and we go to a different wavelength, so it means that we select a different plasma resonance, which can be addressed by changing the wavelength. So in this moment we change the color, the wavelength of the light. Now we are sending green light, so about 500 nanometers in wavelength. And now we repeat the measurement, so we sweep back and forth the magnetic field, and we measure again the variation of polarization. What we see compared to the previous case, that now the jump, the change in polarization is exactly the opposite as before. Before we were going from a positive value to a negative value when we go from positive field to negative field, and now just the opposite. We go from a positive value to a negative value when we go from negative field to positive field. So we reverse the effect. And this is happening thanks to the excitation of the second plasma resonance, which is induced by the magnetoptical activity. So this effect is not achievable using a noble metal nanostructure. It has to be ferromagnetic. And basically, by changing the application of the applied field, the direction along which you are applying it, and the size of the nanoantennas, you can tune the effect as you wish, basically. So you can produce this change at different wavelength, visible, infrared, or UV, and also the entity, the intensity of the effect can be tuned the same way. So What we are measuring here is a reflectivity spectrum, so the signal being reflected by as a sample is a function of wavelength here. So we go from the 400 nanometers of the visible range to the infrared, going up to here. And if you are exciting a collective resonance in your nanostructure, you should see the signature of such an excitation with the appearance of a peak, a very sharp, intense peak at certain wavelength, which is the case here. So basically we see that reflectivity is going up by a factor of 2, basically, a specific wavelength, which is in this case about 600 nanometers wavelength. And this is telling us that at that wavelength, or around that wavelength, we are exciting a collective resonance. So the sample is scattering or reflecting more light. Okay. And the interesting thing here is that this peak is very intense and sharp. Actually, it's a very narrow width, which is comparable to the width you observe in nano elements made of noble metals. But in this case, we are not looking at nanostructures made of noble metal, but we are looking at nanostructures made of ferromagnetic metal. And when you use ferromagnetic metals, due to the much higher losses of the ferromagnetic material, the peak should stretch from the visible near to the infrared, so it should be very broad. So why here we see such a narrow peak, which is peculiar of noble metals? Actually, what we did here, we engineered the shape of our nanoscatterers, or our nanoantennas, and instead of made simple disc, as normally is done, we made them of this more complex shape. We made them as a number of concentric rings. What you can see here, the dark structures are the ferromagnetic material, which is designed to be several rings concentric to each other. And so this fact that we made these narrow magnetic material rings separated by narrow gaps has the effect of producing a plasmonic resonance, which is comparable to the one you have in noble metal. So that's a breakthrough, because one of the arguments against, or that limited the utilization of ferromagnetic materials for nanoplasmonics, was indeed the fact that the resonance were not so defined and so sharp. But now we show that if you engineer the shape, you can make the resonance as narrow as those of noble metals. What you gain here is that the material is ferromagnetic, so you have an additional functionality. You can control the optical properties by application of an external field.